Hey, astronomy. This is Miss Ruark. This is the last podcast for you, Chapter 6. We're going to talk about telescopes some more, and then we'll start using them. All right, so radio telescopes. We mentioned this a little in class. Radio telescopes, there's 4 parts to a radio telescope. A radio telescope has the dish reflector, which would be the dish, right? And it collects and refocuses the radiation that comes in from radio waves. And the antenna here is going to absorb, okay? It's going to absorb the radio energy and direct it along a cable, okay? And then it's going to send it along a cable. It's going to send it all the way through here to this amplifier, which is going to amplify it and make it larger. And then that's going to send it to a computer recorder. Okay, so it'll record all the data for you. Well, why do we need radio telescopes? Why do we need those? Well, the majority of the light that comes in, we already talked about, is only going to be visible light. There's going to be, maybe I'm getting out of that. No. Okay, the majority of the energy that comes through is visible light and the lower end of the IR radiation. The higher end of IR radiation does not come through. It gets blocked through by the atmosphere. A lot of the UV gets blocked by the atmosphere, but radio waves come through. Okay, so we need these so that we can detect the messages or the images that are being sent out, the light that's being sent out from objects that are sending out radio waves. All right, so there are limitations to everything that we have and do. So limitations to the radio telescope is that they're extremely large. Extremely large. They have large wavelengths that they're trying to take in, and the images that come in from these large wavelengths are extremely fuzzy because they have large fringes. Remember fringes? So, poor resolving power. Because they have large fringes, they have poor resolving power and they can't get a good resolution. However, you can combine 2 or more of them to form a radio interferometer. Okay. The low intensity of the radio signals, because radio signals they have a very large wavelength, which means they're low in energy and they have a low intensity. Okay, so the low intensity of these radio signals means that we have to have an extremely large telescope or extremely large dish in order to collect the material or the signals that are being sent in. And it just makes it so that they're huge. Again, we're going back, they're very large. Okay, and then the last one is interference. Now the interference, think about it. These are radio waves. Radio waves are low energy waves. Okay, they're going to be weak in comparison to other waves, they're the weakest ones. Okay, and so a lot of times it can be drowned out by interference. So automobiles have interference when they have a faulty ignition system. The signal can bounce off and give interference. Another example would be the Earth satellites. Those Earth satellites, if they have poorly designed transmitters in them, they can give off the wrong signals and can be picked up by the telescopes. All right, so what are the advantages to them? Why should we use them? Why are they good? Well, they can reveal large clouds or even small clouds of cool hydrogen that's floating around in space. All right, yeah, whoopsie-doo. Why is that important? Okay, well, 90% of atoms in the universe are hydrogen gas. Okay, hydrogen gas is completely invisible to normal telescopes because it doesn't produce a visible light and it doesn't really reflect a lot of light, so it can't be picked up on photographs. But when you have cool clouds of cool hydrogen gas together, this is the place where stars are born. And so we want to see if there's a cloud of cool hydrogen gas in space, because we're going to say, hey, guess what? There's probably a star being born right there. All right, so another example or advantage of these is that radio waves have long wavelengths that can penetrate through large clouds of dust in space. Okay, so they have these long wavelengths. They can get through these clouds of dust. And the clouds, normally if you have like visible light going through, the clouds are made up of dust. And dust will scatter the light. Okay, if you don't believe me, think about it. Think about when you're looking on a in the morning time and you've got the sun coming through the trees, and sometimes you can see the sun. It looks like it's streaming through the trees. Okay, it's called the Tyndall effect, where you can see the rays coming through. Okay, and then the clouds, you know that the light doesn't go through a cloud. It kind of penetrates the cloud. It gets deflected in the cloud because that's when we see the cloud, but it doesn't actually continue to go through. Okay, so it's not going to actually come through and reach the telescopes that we have on Earth. So radio signals, however, will go through. Okay, they will go through and not be distracted. Okay, and we can see them from the other side of the galaxy or further than that. Okay, another advantage is that they can detect objects that are more luminous at radio wavelengths than they are at visible wavelengths. Okay, so here's an example of Jupiter. This is what we see when we look at Jupiter here on the bottom. Okay, that's what we see normally. And we see Jupiter. Okay, but this picture up here is an example of a picture that was taken on a radio telescope. And if you'll notice, you not only see Jupiter, but look at all this other stuff on the outside that you see here that you wouldn't normally see with the naked eye. Okay, that's extra gas and stuff that's invisible to us. It's all radio wavelengths that are coming off of Jupiter that we can't see. Okay, but the radio wavelength telescope will be able to pick that up. Okay, an example of a radio telescope would be this set of telescopes here, the Very Large Array, or VLA, from New Mexico. Okay, in this array of telescopes, we have 27 telescopes, and they're all set up in a Y shape, and it's 36 kilometers across. Now, they can work as individual telescopes, or you can hook them together and make a radio interferometer with extremely better resolution. Another example of one would be the Arecibo Observatory in Puerto Rico. Okay, the Arecibo Observatory is actually the largest radio telescope in the world, and it's so big it's been built into the mountain. You can't move it. It's stuck. All right, and then we have the Byrd Green Bank Telescope up in West Virginia. This one is the largest steerable radio telescope. So it can actually be rotated around on this base, and they can turn it and steer it so that they can focus in on certain areas where wavelengths are coming through. All right, astronomy from space. Most of the electromagnetic radiation that comes, all of the radiation that we have over the electromagnetic spectrum, most of it doesn't reach the Earth's surface. Okay, visible light can come to the Earth's surface near IR, which is just beyond red, so it's the it's the higher IR can reach, but the far IR can't. Okay, so we need telescopes that will help us to observe that radiation. Okay, so the far IR, which is going to be closer to the radio waves, there's a little, if we were to look at the spectrum, and we had gamma rays and X-rays and UV, and then we have visible light here, it's very small, and then we would have infrared, and then microwaves, radio waves, etc. All of those come here. Okay, so visible light can come through. The UV, a lot of it gets stopped in the upper atmosphere, and a lot of these just kind of get stopped in the upper atmosphere. This would be the upper atmosphere here, and this would be the Earth's surface here. Okay, so a lot of these will come all the way down, but most of these up here get stopped in the Earth's atmosphere. They get stopped by just different gases in the atmosphere, carbon dioxide, water. It doesn't come down. So some of this near IR will come down, but then as you start to get into it, it starts to stop up near the Earth's atmosphere. And then the radio waves, the longer ones, will be able to come all the way down. So really, we don't get a lot of radiation on the Earth's surface from the spectrum of electromagnetic radiation. We only get a small part of it here on Earth. The majority of it is stopped up in the Earth's atmosphere, and that's why we need that Earth's atmosphere. It's very important. All right, so far IR, which is going to be closer here, is going to give more information about comets, planets, and forming stars. And it's really important that we study that because we want to know about comets, planets, and forming stars. Okay, now the far IR is absorbed high in the Earth's atmosphere, just like I said, and we need telescopes to be sent up into space so that they can actually read that far IR. Because if we're trying to read it here on Earth, it's not going to happen if it's absorbed in the Earth's upper atmosphere. So we have to send these telescopes up so that they can observe the gamma, the X-rays, the UV, the IR up in space where they're not restricted by the Earth's atmosphere. Okay? And when we send these up, these ones that detect the IR, because IR is all about heat and body radiation, you know, the radiation of body and heat that's coming off, you need to have telescopes that are cool, because if they're not cool, they're not going to detect the warm IR that's coming through. So you have to send telescopes up that can be cooled. And they're looking for stars forming in clouds of dust and gas where visible light cannot escape. But radio waves can escape and IR can escape. They're also looking at black holes, which are extremely small and hard to detect, but the matter that falls into the black hole will give off X-rays. And so you'd have telescopes up that can detect X-rays. Okay, so an example of one of these telescopes would be the IUE, the International Ultraviolet Explorer. And if you said that it detects ultraviolet light, you were correct, because this is sent up there just to find ultraviolet light. It was launched back in 1978, and it actually has a 45-centimeter diameter telescope that it carries around. And it worked until about 1996. Now that was really good because they only expected it to last a year or two, but it actually ended up lasting almost 20 years. Not too bad, right? All right, so telescopes in space, they're going to observe at wide ranges of wavelengths, and they're going to be undistorted by seeing, because seeing is affected by the atmosphere. Okay, they're specialized for their specific wavelength ranges. So we have the Compton Gamma Ray Observatory. So this is a telescope that was sent up into the atmosphere to detect gamma rays. And it was actually, if you can see this right here, is like the window frame. This was taken by some astronauts who were up on a mission one time. They took it through the window of their space shuttle. We also have the Chandra X-ray Observatory. This is a big telescope that detects X-rays. And the Spitzer IR Observatory, which is a big telescope that detects infrared. And then we have Hubble. You guys have all heard about Hubble. Now, Hubble is up there to detect visible light. But Hubble has been maintained by visits from astronauts. So they go up and they fix the mirrors and they fix the lens. They fix anything that's wrong. But the astronauts can't reach the Chandra or the Spitzer. And the Compton was actually removed from orbit in 2000, so they can't do any extra work on that. And I thought this would be kind of funny. I hope you get it. I'll see you in class.